Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel for everything I want to talk about science and math. And today we're starting a new playlist. We're in AP Chemistry, and this is what we're calling the 0 unit because it is background information that you should have, but you might not have. You might have forgotten it, especially if you took honors chemistry 2 years ago, which I know a lot of y'all did. So anyway. Now my quality has gone down of my YouTube. I used to edit the videos and everything, and now I just do it on my phone, and I'll wander out of the shot. My quality's gone way down, but oh well, that's what it is. Okay, so we're starting with chemistry foundations, chemistry measurements, and we're not going to be doing every bit of this, but part of this we'll do, I'm going to leave some blanks because some of this, once I remind you how to do it, you're going to go, oh yeah, and you're going to be able to do it yourself, right? Okay, so what are we in? We are in chemistry, which is the study of substances and the changes they undergo. There are two kinds of measurements that both start with the letter Q. What are they? Yes. Oh, this is so great. I asked honors that today. Dead silence. Did not know. So it's making me happy. Y'all are starting to remember stuff. So qualitative gives the results in a descriptive or non-numeric way. Quantitative, and you can hear the word quantity in it. Quantitative gives the results in a definite form, usually numbers. So in science and chemistry class, we want both accuracy and precision. And accuracy is how close a measurement comes to the truth. Truth is out there. We want to discover it. Okay? But a lot of times we don't know if we're being accurate or not, but one way to help get there is by being precise. And how we can tell if something is precise is how close several measurements are to the same value, or how finely stated. It is. So how repeatable it is. So here I have 3 bullseyes. This one I hit 3 times in the same place, but not the center. Is it accurate?
No.
No. Is it precise?
Yes.
Yes. So this one's precise, not accurate. It's like if you had a really good scale that was messed up and it wasn't zeroed. How about this one? Is it precise? No. Is it accurate?
Yes.
Mixed accuracy. So I'd say accuracy is mixed, precise, no. How about that one? Yes, that's both, and that's what we want. We want accuracy and precision. Okay, good job. Okay, expressing measurements. How we write things is in scientific notation. The reason why is it's a way to write really big and really small numbers. Why? One reason is it's easier, and also our calculators. Our calculators can do math on bigger and smaller numbers than the display can show. So you need a scientific calculator for this class, one that's got the EE button or the times 10 button. We'll talk about that. So how you write a number in scientific notation, the form is you write a non-zero digit. You know how in math X stands for a number, so that's why I'm using it here. And then a decimal point, and then any other non-zero numbers, and then times. And we use an X for times here. I know in high school normally you use a dot or you use parentheses or you use a number sitting next to a letter, but in scientific notation we use an X. Times 10 to an exponent. So for example, here we got a big number. We take our decimal and we frog hop it. We see how many hops it is for it to get to its proper place behind the first non-zero digit. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this number is 1.23 times 10 to the 10th power. Y'all remember that, everybody? Good. So this one, 1, 2, 3, 4, 5, 6 1.23 times 10 to the negative 6. Little numbers are negative, big numbers are positive exponents. Everybody remember that? Good, good, good. See, this is not horrible. So, big number has what kind of exponent? Positive. Little number has what kind of little less than 0? Negative, not just little. Okay, so on your calculators, you should have a button EE, EXP, SCR times to the 10. E means times 10. So everybody look at your calculator. Get it out, and we're going to try putting this number in our calculators. So first we got to put it in scientific notation. Start with this. Count the frog hops. 1, 2, 3, 4. So this is 3.6 times 10 to the 4th power. On this calculator, how you do it is you hit, you put in 3.6, 3.6, the point's down here. The EE is painted on the calculator behind the comma. So you do second comma, and that puts a little E up there, which means times 10. You don't hit the times and you don't put 10 in. The button is times 10, and then you put 4. And the display, oops, I got something wrong here. Why is it doing that? Let's clear that out. Okay, let me try it again. 4. Okay, so the display looks like 3.6 E4. And that means 3.6 times 10 to the 4th. Everybody put that in your calculator, however you do. This one is, 2. Math is more fun with sound effects. 2 times 10 to the 2nd power. So now let's multiply them on our calculator. We hit times, and then we do 2, EE2, enter. And I got 7, 2, and I think 5 zeros. Yep, 1, 2, 3, 4, 5. Everybody got it? Now, why don't you just put in your calculator 2 times 10 to the 2nd power? This is the reason why mathematically. Your calculator recognizes this as one term. Yes?
It has to be in degrees, right?
What?
Your calculator has to be in degrees.
Yes, your calculator needs to be in degrees. If not, go to mode, right here, the button next to quit. That should never inspire you to quit math. Keep going, don't quit. But push the button that says mode, go down and make sure you're in degree, not rad, not radians. Okay? So anyway, the reason why you do this is remember in algebra how you learned about terms. X squared plus x plus 4 has 3 terms. Remember that in algebra? If you put this in your calculator like this, 3.6 times sine 10, raise it to the exponent, your calculator sees this as 2 terms. And if you do the math on it, sometimes you will, on accident, only be doing math on 1 term instead of the whole number. So this is just a place where I've seen kids make mistakes. I've tutored college and high school and taught high school for years and years and years. We don't talk about how many. And I've seen where the kids make mistakes. And I know how to tell you to avoid the mistakes, and this is one of them. If a number can be put in scientific notation, if it needs to be in scientific notation, put it in scientific notation. And you'll avoid some heartache of getting one wrong. All right, so now everybody put this one in your calculator. 1, 2, 3, 4, 5, 6, 7. So this is 3.3 times 10 to the negative 7th. So put it in your calculator, 3.3 EE. And this time, what I want to show you is you do negative, not minus. You'll get an error if you do minus. Do negative 7. And then you divide it by 0.004. You can put that in scientific notation. 1, 2, 3, 4 times 10 to the negative 3rd. So do divided by 4 e negative 3. And you get 8.25, and it says e negative 5. You write it times 10 to the negative 5th. Everybody remember that now? Easy, right? Okay. Next, significant figures or significant digits or sig figs or sig digs. Because I don't know if y'all have realized this, but in science and math, sometimes we're thought of as slightly nerdy. And one of the slightly nerdy things is unnecessary acronyms and things being short. So this gets shortened to sig figs and sig digs. Because, we have to shorten things down. And why do we do this? It's how far to round. Okay, just in case you don't know, how you round is 5 and up, round up. Now, you think that's a little crazy that I told you that. Back a long time ago, like in the 70s, before my time, they had different rules in chemistry for rounding than other math. So if you get to college and they teach you different rules, just know they're out there. I think they've pretty much gone by the wayside. I've told you 3 of my boys are in college right now, all in science majors, and they say they don't have to do the old-timey chemistry rounding rules. Okay, so how do you round? You only look at the digit next to the place you want to round to and round to it. There is a curriculum out there that's used in private school and some homeschool that teaches that wrong. So just know that that's true. Like this big number, you don't look here to round. If you're rounding to this place, you only look here at the one next to it. 7 rounds to 3 up to 4. Everybody good with that? Okay, next idea. Why do we have to know about significant digits? It's because we want to be honest scientists and not make our data look better than it is. So like on your calculator, if you divide 2 by 3, you get 6.666667, right? Everybody's done that? And if you wrote down your answer in a lab, all those numbers down that you got on your calculator, it would make it look like you have the most expensive equipment in the world that goes all those decimal places. That's that precise. And you are at East Paulding High School and you do not have that good equipment. So you have to round it to reflect what your measurements actually can measure. So we don't want to make our data look better than it really is. So how you do this is you do your math. I'm going to write this in all caps using all the digits you have. You don't worry about significant figures till you report your answer. So that means that's easier. That means you can just put stuff in your calculator and carry down the answer. If you have one of these calculators, it'll keep up with your answer for you. And that way you don't have to worry about sig digs till the very end, the significant digits. So that's a good thing. There are teachers who do that wrong. I'll just tell you. So, but these are the rules. But sometimes teachers forget them. Okay, there's 2 different sets of rules. If you had me for honors, you know this. If you didn't have me, you might not have been taught it. So here's a little alert for those of you who didn't have me. There are different rules for addition and subtraction and multiplication. Okay, the rules for addition and subtraction is you go with the number of decimal places with the one with the least number of decimal places. So like you look at it and you see, okay, this number only goes to the tenths, this one goes to the hundredths, and this one goes to the 10,000ths. So what do I round my answer to? I round it to the 10th, because that was my worst answer. You can't put your answer better than your worst answer. Everybody good? Especially the new people? Okay, if not, we're going to do practice with it. You'll get better at it. Also, just a little aside, when I went to my AP Summer Institute, they said if you mess up significant digits, they don't take off but one time. So like you can mess them up through the whole test. They don't take off on every problem. They take off one time and they're done. So this is not something I'm going to stress too much. It's good to do it right, but we're not going to kill ourselves teaching this when it is like 1 point on your test. One itty bitty part. But we want to get every point we can, so I'm going to teach it to you. All right. The rule with multiplication and division is you count the number of significant figures and you report your answer with the same number of significant figures as your number with the least. So, what are the rules for significant digits? All non-zero digits are significant. So, 123.45 has 5 significant figures. Are y'all remembering this? Let's see if y'all can answer these then. Zeros between non-zero digits are significant. So how many does 102 have? 3, yes. Zeros at the beginning after a decimal point do not count. So how many does this one have? 1. Zeros at the end after a decimal point count. So how many does this one have? 6. Zeros at the end with no decimal point do not count. So how many does that one have? 2. Yay! Y'all are doing great. Don't worry, once you practice it, it's easy. Next. Changing between measurements. This is super important to you for the rest of your chemical life. Okay? As long as you're in chemicals, you'll be doing this. Dimensional analysis, factor label, or unit conversions. Okay, so how this works mathematically is unit conversions are things that mathematically equal 1. So things, and the reason why is anything divided by itself is 1. 6 divided by 6 is 1. So as long as the numerator and denominator are equivalent, it's 1. So if I write 7 days over 1 week, mathematically that equals 1. Anything multiplied by 1 is itself. 6 times 1 is 6. It's the identity property from back when you learned properties in middle school, right? So that's why it works mathematically. Do you need to know why it works mathematically? No. You just got to know how to do the problem. But for some of you, you learn better when you understand why. It's just how you work. Okay, so how many seconds till break? We'll say it's 2 days till our break. We'll count the digital day as a break. So you always start with what you, let's see who remembers? No, yes. So you always write what you're given. And you're given 2 days. Whatever you're given is, that goes first. Now, Miss Korn teaches this way, and so do a lot of teachers, but I know you might have thought I was 22, but I'm not. I'm old, and I've been doing this a long time, and I've seen all the mistakes kids make, and one of them is they'll turn parentheses into a 6. So I don't like you using parentheses and fraction bars. I want you to do it as a little train track. So what we're going to do is make a train track. But what this is like a parenthesis, and that's a fraction bar. How you do dimensional analysis is you start with what you know, you take whatever is in the numerator here and shove it to the denominator. And I think it's more fun with sound effects. Math is just more fun with sound effects and singing. So you write just the unit, days, down here, and then you write what it's equal to, the thing that's the same as in the numerator. But I don't know how many seconds are in a day, so I have to go with what I do know, and I know how many hours are in a day, and it's 24 hours is 1 day. These are equivalent, these equal 1 mathematically. When you have the same thing in the numerator and denominator, what are you allowed to do in math? Mark it out. One of my favorite things to do in math, I don't know why, but there's something fun about marking out math. It just is. Okay, but I still don't have the right answer. I have hours, so I have to keep it going. So I push hours into the denominator, ka-chow, more fun with sound effects. And now I think, do I know how many seconds are in an hour? No. But I do know how many minutes are in an hour, and it's 60 minutes is 1 hour. Hours mark out. Now I have minutes. Now I'm getting somewhere. Minutes go to the denominator, and seconds go on top. I know 60 seconds is 1 minute. Minutes cancel out. I multiply any number on top. I divide any number on bottom. And we'll talk more about how to do that and not mess it up on your calculator. Anybody want to do it on your calculator real quick? Tell us what we got.
172,800.
How much? 72 what? 5 zeros? How was it? What is it?
172,800.
172,800. All right, that's how many seconds to your glorious freedom on Friday. Woo! All right. How many centimeters in 4 feet? You can do it. I'll let you practice it. You might need to know that there are 2.54 centimeters equal 1 inch if you haven't memorized that. But you can go back and do that one later. And if you want to see me work these out, they're in the Honors Chem playlist on my YouTube channel. Okay, international measurements. Why do we have them? In science class, we use measurements that can be understood. Oh no, I got too close to it. Let's see if I can do it this way. Oh yeah. My sleeve messes it up. I shouldn't have worn something that's synthetic. Okay, it can be understood all over the world. It's easier. So like my son Nathan is in the PhD chemistry program. He's getting to be a doctor of chemistry at Georgia Tech. He sits there and watches videos from India. He does not speak Punjabi or any other Indian language, but he can understand everything because what they're writing, they're using the periodic table and they're using numbers and units that we've agreed on, and he can understand the chemistry without understanding their words. And he'll watch these videos, and I'm like, that is so weird. He'll sit there and watch Chinese videos and Indian videos and all that, and actually understand them and go, oh, and I'm like, okay. So what is called is Le Système International des Units. I'm sure I said that in perfect French, but because I don't speak French, we call it SI. So we also will call it the metric system. It's not really the metric system. SI and metric are a little bit different, but mostly it's the same. And you should know these units. What is the base unit of length in the metric system? Meter. Okay, do y'all know if I write M, that's meter? Okay, so what's mass? Grams. Time is second. Current. Most of y'all have had physics. What were you measuring that current in? No, that's resistant. It's amperes or amps. Amperes. But you've heard of amps with car stereos and stuff. Temperature in SI. Do you remember that from honors? Kelvin. And what is it in metric? Celsius. Volume. There's two. There is liters or cubic meters. And you need to memorize that 1 cubic centimeter is a milliliter. Do you remember energy? From physics, you should remember this. Joules, yes. Joules. Pressure, there's a bunch of them. One is atmospheres. Another one is millimeters of mercury. Another one is pascals. All right. See? Look how much you know. Okay, and one reason why we use the metric system is because you don't have to do a dimensional analysis with a lot of conversions. And the thing I teach my students to remember this easily is King Henry's daughter bakes delicious chocolate muffins. So this is kilo, hecto, deca, basic, that's your grams, liters, Celsius degrees, deci, centi, milli. You can remember deci, centi, and milli all go together because they all end in E. And you can also notice deci is little d, deca is big D. Everybody remember that? So you can frog hop. So King Henry, everybody imagine him. His daughter, I want you to imagine the princess from Princess and the Frog, because we need a frog to frog hop. So everybody got your king, your princess, and your frog. What's the guy's name of Princess and the Frog who's so funny? Just one kiss unless you beg for more. What's his name? Naveen. Yes, I love that movie. That's my favorite Disney princess movie. Okay, so we're going to change 4,800 kilometers to millimeters. We start at kilo, what we know, and we go to what we don't know, and we count how many frog hops it has. My pen's coming apart. 1, 2, 3, 4, 5, 6. It's 6 hops in that direction. So now my decimal point here, I'll write it here. My decimal point, there's Prince Naveen. He's going to go hopping 6 times in this direction. 1, 2, 3, 4, 5, 6, landing right there. We add zeros to the hops where there is none. That goes back to 3rd grade long division when you learn how to augment zeros. Remember that? So that's the answer in millimeters. That's fun, isn't it? So that's on your test. That was on your review sheet. Any questions about that? Can I go on? Y'all can practice those others on your own. Okay, so we need some math to do so that we can practice doing math and sig figs and all that. So one of the things we talk about in chemistry is density. It's a physical property. It's equal to mass over volume. And I can show you how I want you to do math problems with this. If you have me for physics, I'd make you do them the same way. I'm real picky about this because I have found over the years that kids need a systematic way to attack a word problem. And if you have a systematic way, you don't panic, you think through it, and you get better answers. Okay, so here's our question. What is the density? So my question word goes with density. I always annotate my problems. All the way through my degrees in college, this is what you do. Write on the problem and label everything. Because what makes problems hard is not the math, because your calculator will do it for you, it's the words. So we want to break it down so it's just a math problem. So my first thing is, here's my question word. So density is my unknown. Of a piece of lead, I circle lead because this is chemistry class and lead might be important. That has a mass. Okay, so here's mass. So I identify that's my mass and that's my volume. So step one, I list my knowns and unknowns. So density is my unknown. Mass equals 114 grams. Volume equals 10 milliliters. Then I think to myself, is there a formula I know that relates my knowns and unknowns? Yes, there is. And I write it down. Density equals mass over volume. Because this is showing my work. Now I want to put my numbers in for my letters. So I sing a song. Now you can do math without singing and dancing, but you're not having as much fun as you can have. When I was in ninth, I'd always made straight A's, been in the gifted program, super smart, until 8th grade. And I was in a very bad horse accident. I had a horse named Gypsy, but I wasn't riding Gypsy. I was riding my friend Becca's horse, Buck. He ran me under the barn, got an extreme concussion. Nowadays, when a kid has that bad of a concussion, they send them home for a year and tell them not to think. This was the dark ages of the 80s, and they just sent me to school. I saw double for a couple of months. It was so bad. But suddenly, I was not so smart anymore. And I remember sitting in algebra, looking around thinking, okay, I know I'm smarter than everybody else in here. Why do they understand this and not me? So I was a little arrogant. But at the same time, I had such a hard time learning and remembering. So what I taught myself to do was songs and dances and ways to remember things. And it's come in very handy as a teacher because I can help students remember things. So anyway, the song we sing here ever since I was in 8th and 9th grade is from before my time and your time. It's by The Who, and it's Substitute. So it goes like this. Substitute. So I sing that little song to myself, and I substitute it in. D is my unknown, it's my variable, so I continue to make it a letter, just like in how algebra, you keep a letter. The mass is 114 grams. My volume is 10 milliliters. It's wise to put the units in, because if your units work out, that means you did your math right, and then you do the math. Now, normally you would do this on your calculator, but this one's so easy, I can do it in my head. I'm not concussed right now. When I was concussed, I probably couldn't have done this. All right, so there's the answer, and you have to put a box around it, because I used to teach bad kids in Cobb County, and they would cheat by doing a problem every possible way. You see, they'd take their numbers, they'd add them, they'd subtract them, they'd multiply them, and they would divide them in every order they could think of. Not that they knew how to do the problem, they were just trying to get it on the paper. So you have to have your final answer in box. Any question about how to do a problem? This is great, it's so easy. Okay, moving right along. Now moles. In chemistry class, our unit of measurement is moles, and you should remember that from honors. So, but just a review in case you didn't, this was something you were kind of shaky on. When you go to the store and buy eggs, what unit do you buy eggs in? Do you buy one egg? No. How many do you buy? A dozen. How many is that? 12. So we are used to some numbers like dozen having a name. A dozen is 12. What do you buy socks in? Can you buy one sock? No. Even if you're a one-legged man, you have to buy two. What do you buy them in? A pair. And a pair is another word for two, and two is so special it has another name. If you have a partner, what are y'all called? A couple, right? So this is a very special number, two. It has 3 names. Well, in chemistry, our unit that we use to get chemicals is moles. It is 6.022, or sometimes you see it 6.022 times 10 to the 23rd. And it is so special, it has 3 names. It's also called Avogadro's number. Everybody remembering that? Good. So we can convert something to get the number of moles. So if we wanted the molar mass of nitrogen, where do we look? The periodic table. See how I have M&Ms here? Do you see how I have M&Ms on my periodic table? Because molar mass is often abbreviated MM. So that's my little thing to help you remember where to look. And so if we're going to do nitrogen, there's 2 numbers on the periodic table for nitrogen, 7 and 14.0067. Which one is the molar mass?
14.
Yes, 14. And we're just going to round it off to a whole number here. On the AP test, they have a periodic table that I think that you will use that goes to 2 decimal places. So, any questions about that? Okay, we're going to skip that. You can practice those by yourself, but we're going to do a little problem here. How many grams are 4 moles of carbon? When we do a problem, we start with what we know. And what we know is 4 moles of carbon. So we write 4 moles of carbon. We start our train tracks. We push the unit of what we know, ka-chow, to the denominator. Moles of carbon. What we want is grams. That is our unknown. That's going to go in our numerator. What is the conversion factor for grams to moles for carbon? What are we looking for? 12. Is it 12 grams or 12 moles? 12 grams to 1 mole. Moles cancel out. What is 12 times 4? 48. We could sing the song if we needed to. Let's start out with a 0. 12, 24, 36, 48, 60, 72, 84. Okay, we just had to sing it. Did any of y'all learn skip counting by singing when y'all were little? If y'all did the skip counting songs? Okay, so here are the rules, just to show you the significant rules again. Adding or subtracting, you look at your numbers, which one is the least precise, is 213.6, so we round our answer to the 10th place. Everybody know that now? Because I know that's new for some of y'all, because I know Miss Cornett and teach it. And for multiplication and division, how many sig figs does the top number have?
5.
5. How many does the bottom have?
4.
So how many does the bottom one need to have? The answer need to have? 4. Everybody see how I do that? Okay, good job. Keep it going. Okay, I gotta go to the other page here. All right, so now we're gonna talk about the story of the atom very quickly. We're doing great though. Y'all are doing awesome. We are remembering a lot. Okay, so story of the atom. Uh-oh, I got a phone call. See, once again, my quality of UT. These books. Hello. D-A-M-I. Who in here goes by the nickname D-A-M-I? Oh, that's D. D. It's a her. Yes, D is a girl. And she knows what's going on, and she is going to her bag to get something. Okay, thanks. I was like, all right. Okay. So there's just a little bit of history of chemistry. There was an old Greek guy named Democritus, and he gave us the term, we'll make this bigger, gave us the term oops, we've got a little problem here. Let's see if I can get it to work. Boop, boop, boop. Yep, it's going to work, yeah. He gave us the term atom. Does anybody remember what it means? Which means?
Molecule.
I told you you can say it in the pledge. One nation, atom, for liberty and justice for all. It means indivisible. One nation, indivisible. One nation, atom. He was an ancient Greek philosopher. He wasn't even a scientist. And he figured out, his idea was, he was standing on a beach. And he said, this beach is one thing. But it's really made out of a bunch of little things, grains of sand. I'm one thing. I bet I'm made out of a bunch of little things. I'll call them atoms. So he was right. Isn't that smart? So everything is made of atoms. like a beach is made of sand. But then science went through a long dry spell. And then we had the witches. We had the alchemists. And they were trying to use spells and magic and potions to turn stuff into gold. But they were great because they gave us a lot of the equipment and techniques we still use to this day. So we can't, and really, one of the first big discoveries in science was an alchemist who started us on the road to purifying elements. So we can't totally diss them. But then we came into the modern age with John Dalton, and he gave us the atomic theory of matter. All matter is made up of indivisible and indestructible atoms. And not all of this is completely right now. We've added to it, but it's pretty good. Atoms of a given element are identical in their physical and chemical properties. Atoms of different elements have different physical and chemical properties. Atoms of different elements combine in simple whole number ratios, no fractions. Water's H2O, not H1.5, 2. Atoms cannot be subdivided, created, or destroyed when they are combined in or separated in chemical reactions. Do y'all remember the abbreviation for reactions is RxNS? If not, make a little note. And his was called the billiard ball model. So Democritus's model is that, sand. Billiard ball is like pool. If you play pool, you know, with the pool cue, he said that's what atoms are like. But then they made a cathode ray tube. So that's kind of cool. They had this ray gun, and of course they shot stuff with it. And they were able to figure out that there were subatomic particles that had a charge. So there was a guy, his name was J.J. Thomson, and he knew that there were negative charges and positive. So he said that the atom must be like plum pudding, where it's like negative raisins and positive goo. So there's a positive part and a negative part. And the reason why they figured it out is they had a ray gun. How cool is that? Cathode ray tube. Positive particles can be attracted or repelled by a magnet. He said the plums were negative charged particles and the pudding was positive goo. So he had a friend, Ernest Rutherford, who went to prove his buddy J.J. right. And so his idea was he had a piece of gold foil. It's just like aluminum foil you have at your house, but it's made out of gold and it's much, much thinner. And he took the ray gun and he was going to shoot it, and he thought he'd get a big splat. Because if you took a gun and shot pudding, you would get a big splat, right? Everybody agree? But he didn't. He was so confident of this, he didn't even go to his own experiment. He made his graduate students do it because they had to stand in a dark room and count how many times the ray gun went through the gold and hit the glow-in-the-dark screen behind it. And they had to count the flashes. That sounded dull. Ernest didn't go to his own experiment, made his graduate students do it. But they were totally blown away. Because instead of getting a big glow-in-the-dark splat on the back, it kept hitting the same place over and over and over again. Okay, so he came up with the planetary model. So this is the one we see a lot. It's the Jimmy Neutron atom. And this is the very famous gold foil experiment. Very famous. Okay? It was very shocking. Why? Who can tell me why this was so shocking? What's the atom made out of? That's right, nothing. And it is that the atom is mostly empty space. So smart of y'all to not say anything when I ask you what the atom, why it was shocking. So that is shocking. Just think about it. You are empty space. 99.9% of you is not even here. The only thing that stops me from sticking my hand through my body is energy, not matter. Now, are you a little shocked, like how Ernest was? So he figured out that there was a positively charged nucleus, and the rest of it's empty space. And he named it the nucleus, or what it is in Latin, just like how atoms is indivisible. Nucleus is little nut. I think the Latins are funny. Oh, let's make it sound sciencey. We're going to call it a little nut in the middle. but we want it to sound smart, so we'll call it the nucleus. All right, so then came along Niels Bohr, and you should remember Bohr models from honors. 1913, this is a long time ago, over 100 years ago, he figured out that electrons could only hang out in certain energy levels. Do y'all remember big E is the abbreviation for energy? Good. Okay, the electron jumps between levels, and that jump takes a certain amount of energy called a quantum. Remember the quantum leap? The electron jumping between the energy levels. See my Bohr model over there? Those electrons, there's no stairs between those circles. They have to hop between those orbitals. Okay? So this is the planetary. That one's Rutherford. Here's the Bohr model. There's his. Okay? So now they know about the orbitals. They know about the nucleus. Then Joliot-Curie and Chadwick that were a lab team, and they figured out that there was another particle the same size of a proton, but neutral. So they discovered the neutron. And yes, Joliot-Curie is Madame Curie's daughter and her husband. She hyphenated her name. If your mom is the most famous scientist in the world and you're going into science, you don't want to change your name. You're going to keep some of your name there, right? So that's Marie Curie. She had two daughters. One became a very famous actress. We don't usually talk about her anymore. And the other one became a very famous scientist. So then now the more modern view is the electron cloud model and quantum theory. That the electrons can be thought of as particles or waves. There's a relationship between electron energy and light. So you remember all those light labs you did in honors. And it's not just Roy G. Biv, it's the whole electromagnetic spectrum. Roy G. Biv is, of course, visible light. The whole thing is Ronald McDonald is very ugly, extra gross. Radio, microwave, infrared, visible, UV, X-ray, gamma rays. That good? Y'all kind of remember this? Good. Now, the story of the periodic table. So there are patterns in nature that are discoverable, which is great. That gives us a lot to do as scientists, is trying to discover these things. Well, the scientists, once they started figuring out about the elements, they started realizing there were some patterns. And there was a guy, Dmitry Mendeleev, and he started looking for ways to organize the elements based on these repeatable patterns. So there are repeating predictable patterns if you arrange the elements correctly. Now, did he make the periodic table? No. He discovered the periodic table. These patterns have always been there. Ever since there's been elements, there have been patterns, okay? So he arranged the periodic table by atomic weight because they didn't know about mass then. They didn't know, not really about mass. He did this before the discovery of the proton. So you know right now the periodic table is arranged by the atomic number, and you remember atomic number is the same as proton, right? Everybody remember that good? Okay, so he discovered the periodic table. Okay, so we have a song about it. We gotta sing it because some of y'all remember it. Who told the elements where to go? This is your part. You go, Mendeleev. Okay, so what this is it's a song based on old drinking songs. Mendeleev was a Russian graduate student. Graduate students go to the bar, they drink, and back then they'd sing and play cards. Because women didn't go to bars, usually just men did. So what they did, they'd sing and play cards. So he was, so the song sounds like an old drinking song, and where you've seen this is in Beauty and the Beast. No one spits like Gaston, no one da. That's what that's based on too. So Mendeleev's song, because he wrote the elements on playing cards, shuffled them until he figured out the pattern. Okay, your part is Mendeleev. You ready to go? Who told the elements where to go? Mendeleev. Who put them down in columns and in rows? Mendeleev. This is a pretty part. Who was willing, who was able, You can sing along if you want to make a periodic table. Who told the elements where to go? Mendeleev. Okay, so we're going to do it one more time with more enthusiasm. And at the end, you're going to take your pretend apple juice, not beer, and toast Mendeleev. Okay, you ready? Who told the elements where to go? Mendeleev. Who put them down in columns and in rows? Mendeleev. Who was willing, who was able to make a periodic table? Who told the elements where to go? Mendeleev. Yay, Mendeleev. So this was a big moment in chemistry, as you can tell by the song. Okay, so then it was wrong because it was by weight and not by atomic number. But then they discovered the proton, and there was a young guy named Henry Moseley, and he rearranged it by atomic numbers. That's not just a hashtag, that is a symbol for number. The whole number that tells you how many protons. He was real young, he was like 26. It was World War I, he was in graduate school. He signed up to go to World War I, and his professors were like, no, you are the smartest person ever. You are England's most wonderful national treasure. You can't go to the front. So they wrote letters and said, this is the smartest person ever. Don't send him to the front. So what did they do? And when did he die? Almost immediately. They said he was smarter than Einstein. Like he was, instead of calling a smart person Einstein, you would call him Moseley. But instead, he got killed. So they made a new law in England that if you're a good scientist, you do not go to the front. You get to go do science for your country. But it was too late. So there's Mendeleev's playing cards. And then the last one to change the periodic table was Glenn Seaborg. He put the part on the bottom, the actinides and the lanthanides. So he did the bottom section. Okay, and by pulling those out, it makes it better. Okay, the story of radioactivity. There's a guy, Henry, but I've also heard him called Henri Becquerel, and he accidentally discovered radioactivity. We got a little bit of time, good. Doing all right. So he was working with glow-in-the-dark rocks. Because, that's fun. We like to do fun things. And he was seeing if glow-in-the-dark rocks make enough light to take a picture. So he had photographic plates. It was the weekend. He put his rocks in the drawer, closed it up, went off, came back, and on Monday when he was ready to continue his experiment, the rocks that were wrapped up completely exposed the photographic plates that were in a dark drawer wrapped up. Very shocking. Turns out those rocks had a little bit of uranium in them, and so what he discovered was X-rays. And they didn't really know much about it. They certainly didn't know it was dangerous. They would take X-rays of people walking and see their skeleton walk along. You see it in really old cartoons, the skeletons dancing and stuff behind the curtain. They really did stuff like that. Okay, Marie Curie, I told you she was famous. She was friends with Henri Becquerel, and she was the first one to really understand radioactivity, did experiments, figured out that the nucleus was giving, nucleus that these radioactive things were giving off particles. Her husband died. He was hit by a taxi cab back when it was like, in the 1900s, but like even in Atlanta, you could get a horse to pull you around the town. Even in Marietta, they have that. So it was one of those. And he got hit by one of those horses, and he died. So women were not allowed to speak to the scientific community, but she was the only person who did, so they let her come speak to the scientific community. She was the first woman ever to do that. She became extremely famous. She discovered two elements, radium and polonium. Then Lisa Meitner, this was in World War II. She worked with Otto Hahn and Fritz Strassmann on radioactive elements. They had some radioactive elements. They were shooting it, with these ray guns. You got a gun. What do you want to do? Shoot something with it. And she was Jewish, so they had put all their money together and got her out of there because Hitler was in charge. He was killing Jews, and so she went to safety in Switzerland. And they were still sending her their papers, and on accident they split the atom. They didn't understand what they did. She did, and so she discovered nuclear fission by understanding that. So she figured out they had split the atom. Sometimes she's called Lisa, sometimes she's called Lisa, sometimes she's called Lisa. I call her Lisa. Nuclear fission, splitting the atom, as opposed to squishing the atoms together, that's fusion. Enrico Fermi, let me get back to here. He was the first person to control a chain reaction. And all of this led to the atomic bomb for World War II. Okay, so the atom. Protons have what charge? Neutrons? Negative. Electrons? Negative. Protons and neutrons are big. They are in the nucleus. Electrons are little. Okay, so let's do a Bohr model. Let's see if you remember. The Bohr model, we'll do lithium. So first of all, you can draw circles, or you can write how many. We'll just write how many. How many protons does lithium have? How many? 3, because this is its atomic number. How many neutrons does lithium have?
4.
You round that up
4.
to 7, subtract 3, and it's 4. Okay? Now, here's the first atomic energy level. Do you remember how many electrons it gets? 2. So we could draw 1, 2, and then the next one will go on the next one. And you can see I'm written under my Bohr model 2, 8, 8, 18, 18. You really don't go that far. Bohr models only work, remember it's from 1913, this is old science. It really only works up to number 20. After that, you don't really do Bohr models. Okay, ions. If an atom gains or loses an electron, it becomes what? Let me see how I wrote that. Isotopes, ions. Okay. If an atom loses electrons, is it positive or negative? It's going to become positive because it lost some negative. So this is that called a cation or an anion? Cation. And how you remember that is because cats are wonderful, sweet creatures. There's our cats over there for you to remember how wonderful and sweet cations are. Also, we are remembering that metals from that side of the periodic table are the ones that make cations. If it gains electrons, it becomes negative, and it is an anion. And even if you're a cat hater, you got to admit that cats are better than fire ants. So we see the fire ant on the other side. I know fire ants aren't really red, but it's more fun. And that the things on that side of the periodic table become negative. Everybody remember that from honors? Good. Okay, so if we have an element, we can know its atomic number. So say we've got, I'll draw one for you. We'll say, okay, so I have a positive potassium. Its atomic number is 19, and we're going to say its mass, who's over there close? Lily, what's the mass of potassium over there? 39?
39.090.
Okay, we're going to say it has a mass of 39. Okay, so if we look at this, the atomic number is 19, the number of protons is 19, the number of neutrons is 39 minus 19, which is 20. The atomic mass is 39. The number of electrons is what? It has a charge of plus 1. 18, because it lost 1. Is it an atom or an ion? It's an ion. It has a charge. Ions are charged atoms. Now, what's an isotope? Atoms can have more or less neutrons. They can be fat or thin. That's our cats over there, too. See how we got Ruby? Ruby is fat. Tigger is skinny. These are my cats, and they have the same diet exactly. Tigger runs around like crazy man and exercises. Ruby does not. So it's a cautionary tale about the need for exercise in your life. Okay? Some isotopes, especially fat ones, can be radioactive. So how something has more or less, how things are isotopes is they have more or less neutrons. When they fall apart, they become radioactive and they shed atomic particles like alpha, beta, and gamma. Is that it? Is that all I gave you? We at the end? We got more? What's it got? It's probably something I gave honors that I didn't give regular. What's it got? Oh, okay, y'all know that. You can color the periodic table all by yourself. Anybody need to know where any of this is, or do you know it? You need to know it? Okay, let's show you. I want to give y'all time to look at your study guide and see if you have any questions for me, but I'll throw this up there. Let's go to the desktop. Go to all right, so here it is. So these are the alkali metals. Let's make it bigger. Okay, first column alkali metals, second one alkali earth metals. These are the transition metals. Lanthanide, see how lanthanum is on the top? So that's easy, lanthanide. Actinides are down here, see how that's actinium? Okay. The halogens are right here next to the noble gases. That is what one of y'all remembered day one when I asked you what you remembered from honors. The other metals are right here because the stair step separates metals from nonmetals. The things that touch the stair steps are metalloids. There is debate among the scientific community about exactly which of those are metalloids or not. You could just say that all of them that touch are. If you go into the Army and become a scientist for the Army, they will disagree, okay? These are the nonmetals over here, noble gases at the end. Good? Yay. Okay, so get out your study guide and you can ask me anything you never got the answer to. I'll tell you the answer. Oh, so that's it for the video. Like, share, subscribe. Science is great.